Go ahead. I mean, if you did, yes, that's great.
I know.
But
5-5.
we just want to do them now. 5-5 is what we're doing right
I
now.
already did the notes for that one.
Good,
I'll
but
just
you
take
need
one.
to take classes,
Yeah.
notes in class. Okay, lesson 5-5. This is about ratios.
Plus ratio.
Okay, a ratio is different than a rate. Okay, remember yesterday we talked about rates. Rates have two different units. So examples, miles per gallon. Notice the units are different. A mile is different than a gallon. Okay, so that's what a rate is. There's always two different units. The only difference when we talk about a ratio has the same units. A ratio is just like a rate, except for now the ratio has the same units. So it might be a number of cups of concentrate to the number of cups of water. So if you work outside or any of that kind of stuff, you can work with fertilizers. A lot of times they come in concentrates and you put so much of it in your water. Okay, so that's a ratio, when you're putting the ratio of the fertilizer to, or the concentrate to the water. Orange juice, if you buy frozen orange juice, it comes in a can. So a lot of times we do orange juice as 1 can to 3 cans of water. Okay, so that's what a ratio is. A ratio is how many of certain things. So it could be the number of cans of OJ divided by the number of cans of water, because that's how they actually specify it. Okay. Ratios might be of boys to girls. They're people, so the unit is a person. Okay, but we might have the number of girls to the number of boys. Okay, still the unit is a person. Okay, so both units are the same. Okay, so ratios are like that. Those are all ratios. Okay, same thing. So they're different than rates, but basically a ratio is used just like a rate. Okay, but usually what we do it is, instead of converting between different rates, which is what we did yesterday, okay, we use ratios to find out how much. So let's say our ratio of concentrate to water is 0.25 to 8. Okay, 0.25 to 8. So you put a quarter cup in 8 cups of water. Okay, so let's say I'm going to make a gallon of water, 1 gallon. Well, one thing I need to know is how many cups are in a gallon. Does anybody know? You have to convert it.
Oh.
Oh, 4.
No.
No.
4 cups are in a quart.
Yeah. That's
How many
what I was
quarts are in a gallon?
No, 2.
gonna say.
4. So how many would that be?
That would be 8 cups. Oh my.
No.
It's not 8.
No, it's
What am I
4
on?
times 4.
I should know.
Right.
4 times 4.
Which is
16.
it's 16 cups. So 1 gallon is equal to 16 cups. Okay. So if we were doing that, this would be 16. We want to know how much concentrate I'm going to put in it. Now, hopefully you guys can figure that out. If I double the amount of water, how much do I put of the concentrate? It's a quarter cup right now. How much am I going to put? So I doubled this, right?
You doubled that. So you're gonna put
What am I going to do with
0.5.
this? Yes.
0.5.
0.5. You double this one. And a quarter time plus a quarter is a
Half.
half, which is 0.5.
Or you could do 0.25 times 16 divided by 8.
You could.
But that's a long way.
That's the long way on ones like this, okay? So now let's do it weird, and let's say instead, we have some oddball sprayer that we're gonna spray it out of, okay? And we have, it holds 60 cups of water. Now what he's saying works, because if we don't see, 8 does not go into 60, we can't divide it, okay? So when you're solving ratios, multiply the two that are across from each other. This is called cross multiplication, okay? So the two that are cross, so you would multiply 0.25 times 60, and then you divide by the one that's all by itself. It doesn't have anything across from
It'd be like X.
Yeah,
Yeah.
okay, and that will give you X. Okay, so 0.25 times 60 divided by 8, what would it give us?
1.875.
1.875 cups. What is 1.875 cups? Does anybody know?
Rounding up 2 cups.
It's 7/8. Okay, that's 7/8 of a cup. Okay. So that's where you have to, so this is where decimal conversions and memorization of those numbers, it makes it very important to do those. Mason, do you have your cell phone out?
Oh, I have it down here.
You don't have it down there?
I have it right here on my.
Okay, could you please put it away right now?
Oh, my leg.
Put it away, please. In other words, I will take it if you otherwise, okay? So make sure it's put away and it stays away. Okay, in class we don't use cell phones. That's campus wide.
Yeah.
Those are the rules. Okay. Even having them out, it's using them. Okay. Okay. So this is another way to solve it by doing the cross multiplication method of solving it. Okay. So in this class, we have a ratio that is of boys to girls, okay, or girls to boys. It is 2 to 5. 2 girls to 5 boys, okay? If we kept that same ratio in a class, okay, if we kept that same ratio, and let's say we had a class of, this is a really big class, of 36 boys, how many girls would there be if we kept that same ratio?
14.4.
How did you do it?
2 times 36 divided by 5.
Okay, 2 times 36 divided by 5, whoops, is how much?
14.4.
And because we don't round girls, it would be 14 girls. Okay, so that's about the same ratio. Okay. What if I looked the other way? What if I said I had 2/5, 2 girls to 5 boys, and I have 17 girls? How would I do that one? How would I find the answer to that? Yes.
You would do 5 times 17 divided by 2.
So you multiply again the ones that are across from each other, that's cross multiplication, and divide by this one. So you do 5 times 75, which I believe is 85.
Wait,
Divided
5
by
times
2.
17.
I mean 5 times 17, which I believe is 85. And that would tell you how many girls you have, boys, how many boys would you have?
42.5.
Well, again, we would round down because you can't have a half a boy.
You can
Okay, that
have
would be very
another
hard.
boy.
Oh,
You can
don't
have
even.
43.
Okay, no, we're not gonna go there.
I don't even know what you meant.
No, we know what you meant.
I don't know what you meant.
That's a lot.
I don't get it. I'm not gonna want to get it probably.
Okay. Are we taking notes, Mason? Take notes. Participation in class is notes. Okay, so that's basically the same thing with ratios. Now, I'm just going to show you a couple other things. To me, ratios and fractions are the best way to write them. Okay, they also write ratios this way. So 2 to 5, that's girls to boys. So you can write it with just a colon in between them. That's the same thing as 2/5. I like the fractional method because it's easier to read, but you will see concentration sometime written like that when you're doing, maybe your cleaner is, so a lot of times you buy, like I buy Simply Green, it's a concentrate. And you mix it with water and then you use that. You don't want to use it full strength. You have to actually dilute it and stuff so that you do that. Your dad in his business, I'm sure, mixes weed killer up. It comes concentrated. He takes a certain amount of that and mixes it with so much water. That's a ratio that you're doing there. Okay, so those are the kind of things that are where we use this. So this is used a lot. It's actually used in recipes. Okay, there's some recipes that I know that you put 1 cup of orange juice to 4 cups of I'm trying to think, fruit punch. Okay, and that makes a punch, so you can do that. So there are some, and so that way you can make whatever amount you want. So if you double it, you get 2 cups to 8 cups. Okay, so you can, it's really a ratio when you're doing recipes. If I'm making, if it says a 1/2 cup of flour to 1 cup of sugar, which would be very sweet, okay, then if you double it, it's going to be 2 to 1, okay? So it's doubling it because that's what we do with recipes. We cut them in half, we build them up, that's all a ratio. Because a recipe is really a ratio. It's a whole bunch of ratios. This is how much you put of each ingredient. Those are ratios that we want to keep consistent if we want to double or triple or have the recipe. So we have to keep those consistent. Okay, so that's basically all about ratios. Okay, I have to find what chapter we're on. Oh, here we are. Okay. Okay, so the next thing we're going into is 5-6, which is again really just a use of a ratio. Okay, 5.6 is a ratio that we define as the probability. Okay, so the probability, we're talking about probability. I'm sure you've heard the probability of snow today is 10%.
Wait, really?
No.
I've been reading my dreams.
No, mine would be 100%. That would be my dream. Okay, so probability. What probability is defined as? So it is a ratio, and it's equal to the number of the specified amount the specified event over the total possible events. Now, I know that sounds, okay, that sounds really, really complicated, but it really isn't, okay? Let's just think of a penny. If I flip a penny, what are the total possible outcomes? Well, what are the outcomes that are possible? I flip a penny, yes.
Heads or tails?
Heads or tails, there's only 2 choices.
Or
Heads or tails.
it lands in the very center.
Very unusual, I have seen that occur once. But it is.
I've
is
seen it
done.
occur several times.
I've seen it in a movie.
Okay. So, there are 2 possible ways that a penny can appear, as a head or a tail. So the denominator in our ratio would be 2. So if I said, what's the probability of a head? So here, the specified event is a head, getting a head. Well, look at how many ways. Out of those 2, one way gives us a head. This is so simple, it's almost complicated. Well, the probability is 1/2 when I throw a penny that you'll get a head. Okay? So that's the probability. That's the theoretical probability. Okay?
Although there's other factors into
We'll
it.
talk about it, yeah. Okay, so let's talk about a dice. Okay? How many ways or how many possible outcomes if I throw a single dice are there?
6.
Yeah, we can get a 1, a 2, a 3, a 4, a 5, or a 6 when I throw it. So these are the possible outcomes. Okay, so on the bottom, my total possible outcomes are 6 different ones. Okay. If I want to get a number that's divisible by 3, okay, a number that's divisible by 3, how many of these outcomes are divisible by 3?
3?
2 of them, right?
No, but
3 is divisible by 3 and 6 is divisible by 3. Is that correct?
yeah, that's true.
So out of these outcomes, there are 2 possible that are divisible by 3. So notice how I have to specify the event. I have to say what I'm putting on top. What is the event I'm looking for? I want to get a number that's divisible by 3. So 2/3, or I could reduce it down to, 2/6, or I could reduce it down to 1/3. Or I could make it into a percentage, which is divide 1 by 3, and we get 0.33 repeating, which the percentage is 33.3%. Okay. So we can write it, once we get the fraction, we will see all of these different ways of writing probability. Okay, I like the ratio method the best, it's the cleanest, okay? But we always do percentages a lot because we're trying to explain to people. People understand out of 100, okay? And sometimes it's hard to say if I say 1 out of 17. I don't know what that means. That's harder to know as a percentage or what that equals. What's that going to equal?
0.058823529.
Give me the percentage.
5.8%.
5.8%. So 1 out of 17 is 5.8. That makes a lot more sense to me because I know what 5.8 out of 100 is. 1 out of 17 is harder for me to think about and visualize. Okay. So that's what a lot of times what we do. The reason we have percentages are to change fractions into ways that we understand because it's out of 100. Okay, so that's why we have those. So that's basically, let me make sure there's nothing else in here. 5, 6. Oh, they have, okay. Okay, so. Okay, so sometimes these probabilities we are calculating right here are based on theory because we look at the number of outcomes. Okay, so this type of probability is determined by actual counting. Okay, and we know how many ways give us on the bottom, how many is specified. So this is by actual. These are actual. They're called theoretical. They're called theoretical. They're based on a theory, based on what we can do, we can see. Okay. Another type of probability is based on experimental. And that's where basically you take a penny and you throw it. And you throw it maybe 100 times. And you see how many times you get a heads.
I feel like we did that last year.
We did, okay? It doesn't always, theoretically, it should come out to a half. But in our experiment, it will come close to a half if we do enough trials. It will come out to a half. But we have to do many, many, many trials for it to come out to be a half. So it's based on
Perfect conditions,
design.
it is half.
Yes. So what we can do, let's say we want to look at where we throw 2 dice. Okay, so we could do it experimentally, and if I throw them, let's say we have, so if you think about 2 dice, I'll have to write this out easier. Theoretically, we would have a 1 with a 1. So this, let's say it's a red and a green dice. You have to think of them as being different. Okay? So because we can't, 1 and 1 is not just the same thing. It's each die has the possibility of being a 1. Okay? So these are the different outcomes if I throw 2 dice. We're going to make a nice little chart here. Okay, so we're throwing 2 dice. That's not how you spell it. Actually, I'll have you guys figure out what it is. Okay, so we're going to have red and green. You put the numbers that go in with those. Red and green, red and green. This is going to have 1, 2, 3, 4, 5, and 1 more. 6, red, green, red, green, red, green. Okay, I'm going to write this down. 2, 3, 4, 5, 6. Okay. These are going to be the possible outcomes.
You want us to write this down?
Yep. Now we're going to look into different things. We're going to use it to count up our theoretical, and then if we did an experimental, how it would be. Okay. So if I throw a 1 on my green, oops, I did this wrong. I'm sorry. I lied. This will always be 1s all the way down. This will always be 2s all the way down. This will be 3s all the way down. 4s. 5s. This is the easiest way to figure it out. 6s. Okay, so in this turn, I always roll a red 1. What are the possible numbers that could go for green in that choice?
2, 3, 4, 5, 6.
It could be a 1, right?
Yeah.
Because the red and the green could both be run. This could be a 2, this could be a 3, this could be a 4, this could be a 5, this could be a 6. So if I do a red 2 all the way down, what are my choices for green?
Same thing.
Okay, so fill out your chart. All the different ones. I'll do it while you guys are doing it.
This isn't getting confusing at all.
No, not at all. So if I throw a red 1, I get a green 1. Or if I throw a red 1, I can also get a green 2, right? So those are all the possibilities, because if I have a 5 on the red, it could be a 1, it could be a 2, it could be a 3, it could be a 4, it could be a 5 or a 6 on the green. Okay, how many total outcomes are there?
Or 36.
There's 36 total outcomes, okay? There's 36 total outcomes, because if I count all those, there's 36 there, okay? Sometimes what we do is we say, okay, what's the probability of getting a certain sum, okay? So we're gonna look at what's called a frequency chart. So this is the sum of the dice. Okay, and this is the number of possible occurrences. Okay, it should, well, we know it's going to equal 100%. Okay, we should come up with 36 when we're done. Okay, because they shouldn't give more than one sum. If I add two dice together, do I get more than one sum? Okay. What's the smallest sum when I throw two dice?
2.
2. Okay. So we know we could get a 2. What's the largest sum when we roll two dice? 6, which is what?
12.
So we're going to have everything in between. 3, 4, 5, 6, 7, 8, 9, 10, and 11. I'll move that one up. Okay. Well, this is kind of fun because it actually has a pattern to it. Here's my 1. The sum of 2 is how many possible dice, how many possible ways can I roll the sum of 2? Look at it. One way. The only way is if they're both 1. There's only one possibility there. So this is 1. Okay. How many ways can I get 3? So here you're drawing. Which numbers give me 3?
2 and 1, 1 and 2.
Yes, the 2 and 1 and the 1 and 2. Okay, so there's 2 possible outcomes, right? Okay. What about 4? How many ways can I get 4?
1 and 3 and 2 and 2 and 3 and 1.
Okay, look at this vertical right here. Ooh. There's my 4s. How many are there? 3. Okay, what about 5s?
4, 1, 3, 2, 2, 3, 1, 4.
That's right here. This section right there is 5. There are 4 of them. So go ahead and finish your chart.
So that means there's n less as. Wait, no, that's not right because it doesn't increase. It goes up and then goes down.
No,
Yeah, this is an interesting graph. It actually
I
is
see a question.
parabolic.
What would the?
I mean, it's a quadratic. Sorry, it's a quadratic.
What would be the equation for it? Because I've never seen this.
We just made it.
No, this is the possible outcomes. Okay. So now, if we look at that, we can actually give probabilities because how many outcomes did we have altogether? 36. So our actual probability is 1 out of 36 or 2 out of 36 or 3 out of 36 or 4 out of 36 or 5 out of 36 or 6 out of 36. Whoops, that's not a 6. But then we go back to 5 out of 36.
So 7 is the most likely
Yes.
number.
Yep. 3 out of 36, 2 out of 36, and 1 out of 36.
Could we make something? Could we make something like this for like a D20?
A D20.
Yeah,
They're playing.
For a 20-sided dice.
Yes.
Oh,
Yes.
So what would be the most likely for?
I don't know. You'd have to show. So you'd have to. Well, each one. If you only have one, there would be only just 1 out of 20 for each number. If you only have one 20-sided dice, but if you have two
Two,
20-sided dice, then you would actually have 400 outcomes
Dang.
because it's 20 by 20. This
Well,
has
what's the
6
most
sides.
likely? What's the most likely?
The one in the middle, the 10 and the 10.
But there's no middle. There isn't.
Yes.
There's a middle in
Oh, this
6.
isn't the middle.
So 7 is in the middle.
7 isn't the middle.
6 is.
No, it is the middle if you look at it.
2,
7
3,
is
4, 5.
from 2 up to 12. You'd have to list how many outcomes there are because with the 20 it would be start at 2 and go to
Well, 6. No, 6
go to
is in
40.
the middle.
No, it's not in the middle because there's no 1.
Oh.
So this is the
7
middle
is
number.
the middle.
So it would go from 2 to 40, so it would be not 20, it'd be 21. That's the most common.
Ah.
Okay. Oh, I keep
'Cause
thinking
then-
I only have.
It's got to be one more because it
Yeah.
shifts
Okay.
down.
Yeah.
Okay, so that would be, if you don't understand what we're saying right now, don't worry about it. We're talking about something else. But this is what and then you can write these probabilities as fractions. When I add these up, what do I get?
100.
If I added those up, I'd get 36 out of 36, wouldn't I?
Oh yeah.
Because aren't there 36 outcomes here?
Yeah.
So these are all the different outcomes. So I would add these up, I would get 36 out of 36. Probabilities always add up to 1 of each event. They always have to equal 1.
So
If you put them as percents, they would have to be 100%.
is that 6 factorial plus 6 factorial?
No, it's just 1.
No,
Well,
I mean
it
like
kinda,
the 36 to get that.
yeah, it's 1. 6 factorial over 6 factorial is 1, but that's not really what we have here.
Well, I thought factorial was adding 1 plus 2 plus 3 plus 4
So your
plus 5.
times even.
You'll get there eventually, Matthew.
I mean,
You times them. 1 times 2 times 3
Oh.
times 4 times 5 times 6. That would
That's
actually
power
equal
of.
1. Yeah. So that's what probabilities are. This can be called, this is a theoretical distribution. This is called a probability distribution, and it shows you how likely something is to occur. So this is called a probability distribution. So in practicality, that's true because we've looked at all the outcomes and we've analyzed it. So that's all theoretical. If I were to throw 2 dice, I wouldn't necessarily get these same ones if I were to do an experiment. Okay? So when we do things that we can't count all the outcomes or we can't figure out how many there would be of outcomes, then we do what's called experimental probability. Okay? So an experimental probability is when you perform an experiment and you put down how often things occur. So let's say you have, and I'm going to give you the one that's in the book because we're going to look at that, but so one of the things we have is we don't know exactly how many people have certain types of blood. We know there are just certain types of blood. Okay, do you guys know your blood type?
no, I've always wanted
Anybody?
to figure it out.
I think I found out last year and then I forgot. I think we did this in class and I was like, yeah, that's cool.
Okay, so these are the different ones that you have. You can be O positive, you can be O negative, you can be A positive or A negative. And this all depends on what your parents are and then the probabilities of getting that from based on your
I think
parents.
I'm O positive because
Okay.
my
There's B positive,
Isn't A
And
plus
B
like the best kind of blood?
minus.
AB positive is the rarest.
AB,
O
no,
negative
AB positive is not the rarest. Okay, AB negative is your rarest kind. Okay.
O negative is the best kind because it's the most common.
Okay, so
It's the universal
what we've
one.
done is we don't know exactly how many people, we can't go and find out how many people actually have this type of blood. So we've done counts. We find out what are blood types of many people. And from that, we have done the counting of it. So we have a count. And we know how many times the number of people, okay? So each one would fit into one of these categories. So the number of people, the counts would add up to the number of people. Based on that experiment, because we had to actually count people with these, and we had so many people that we used to count, based on those counts or that experiment where we do counts, then we can come up with what we call a frequency, how often it occurs. This is our frequency. And we can come up with what's called a relative frequency chart. Okay, this is based more on an experiment. We can't actually count every person and see what every person is. So we actually make counts of people. That's really the basis of statistics. We start doing this with statistics, and that's how we come up with different statistics. So this was done as a statistical study. They went out and counted people, how many
Took all
people
their
were,
blood.
took their blood types, okay, found their blood types, which isn't hard anymore because you can
Blood
you
draws.
can get it on blood draws and stuff, okay? So this is what they came out with. 38.4% are O positive, okay? O negative is 7.7%. A positive is 32.3%. A negative is 6.5%. B positive is 9.4%. B negative is 1.7% of people. AB positive is 3.2% of people. And AB negative is 0.7%.
I
It's
see
less
you
than
squished some of them
1%.
together,
I know I
tried to
did.
lengthen it, but didn't work. So
I know, it works. If I added all those up, that should equal to 100%. Okay, because you fall in there somewhere. These are the only types of blood you can have. So you fall in there somewhere. Okay, but this was done by taking people, so it might not be the actual people, but the records of people from like hospitals or whatever, and they count up how many of them are O positive from their blood samples, how many are O negative, so they can actually calculate it based on actual data. Okay, so an experiment is where we collect data and then we make predictions. Those predictions are going to be pretty accurate if we do it enough times, if we have enough people that we're looking at. Okay, so find it. Does anybody know what they are? I'm an A positive, so I'm in 32.3%.
I would assume that I'm O positive because my dad is O positive.
Yeah, that probably, and I can't remember how that works. I don't know which one's dominant when we do that. So yeah.
I'm pretty sure I'm AB positive.
Oh, are you really? Okay.
Rare.
You're a donor then. Are you the universal acceptor? You're the universal acceptor. O positive is a universal donor. It can give to anybody. And so that's why they always want O positive blood. So there are some that can mix with all of them, some cannot. And so that's kind of interesting. Some can receive all of them, some cannot. This one, they can receive, I think it's the AB positive or the AB negative, I'm not sure which, can receive everything. One of them's the universal receiver, they can get blood from anybody, and one's the universal donor that can give blood to everyone, and I can't remember which one's which right now.
So if you know what someone's blood type is,
Yes,
and you give the opposite of what they are, so it's like kind of poison to them, you can put a dart and get a little bit of blood on them, so when you shoot it at them, it gets into their
I
blood.
suppose you could, I suppose you
What would
could.
it cause, a heart attack?
What?
I'm not
I
thinking
don't know
dark.
what it would
I'm
cause.
just thinking that.
I'm seriously, I don't know what it would cause, I really don't. I'm just saying that I don't know if one little spot of it would ever cause a problem, but if you did a transfusion, it would be enough that it rejects it. And then your body would be fighting it, and what happens with that is then it will actually kill good cells along with the bad cells that it's fighting. And so that can happen. That's what happens in transplant. When you hear that a transplant is not being accepted, it means that the transplant, the body's figuring out that it's not its own, and the body decides to reject it. And so then it rejects other things in your body. And so you can actually have a successful transplant, but you die because your body decided to reject it for some reason. So that's why they have to check a lot of things to see. Okay, so
Wait, in a
I
heart
have a-
transplant, do you die for a little bit?
they put you on, yeah, your heart is stopped where they transplant, yes. So I had a nephew-in-law that had a bone marrow transplant because he had leukemia. The first year he did really well, then his body decided to reject it. He lived for 11 years, but the whole time his body got sicker and sicker and sicker because it was attacking everything that was good also. And so he ended up dying because, not because he had cancer, cancer was gone. But the bone, the marrow he got, and he got it from his brother, you would think they'd be a match. Okay, but his body rejected it and slowly it killed him over time. It doesn't automatically happen right away, but it slowly
Why
kills
didn't
him.
they get a new bone marrow?
You can't, once you've done one bone marrow transplant, you can't do another one. It's all mixed in there now, and you can't remove all that, so you just can't do that, so.
So he was bound to die.
Well, the probability that he would die younger than, regular
You
old
said
age.
he lived to the age of 11.
No, he lived 11 years
Another 11
after.
years.
He had kids. His daughter was born, his last child was born 3 months before he was diagnosed. She is now 11.
She is now 11.
She is now 11 because actually she's 12. He's been gone for a year. But he lived for quite a while, and the one nice thing is he had the best attitude because he knew where he was going. He knew that God had him in his hands, and he was given 11 years to be with his family. So we have to look at the positive things there. It's very sad. Are my nieces and great nieces and nephews sad? Extremely. Is my niece sad? Yeah, she lost her husband and now she's a single parent. Very, very sad. But they do know where he went. We know where he went because he was God's child. And he had a peace that actually my other great nieces and nephews have seen. And some of them are accepting Christ because of that, which is exciting because they say, I want to have the same peace that Matt had. That was amazing that he had that amount of peace. And so we can talk about why he had that peace.
You're a grandma?
So, I'm not a grandma yet. I do have grandchildren, and I have step grandchildren, put it that way. I have step grandchildren. My husband has grandchildren. My kids have not yet had kids, so I'm not. But great nieces, those are like my nieces and nephews' kids. I'm a great aunt, many times over.
So you're, wait,
Oh my
how does that,
How does that work?
how does that work? How do you, I forgot about the how nieces and nephews work.
Okay, so here's
Your
your mom and dad.
Look, Matthew.
Mom and dad have children, okay? They come together. In my case, I have a brother, I was my brother, and then there was my sister. My brother had 3 children.
I get it now.
Those are my nieces and nephews. Me, I had 2 children, okay? These guys are cousins. Then, these guys have children. And these are my great nieces and nephews, because these
And
are
those
my
are-
nieces and nephews.
Okay,
Okay, so that's how that works.
thank you for the explanation.
Because mine don't go down any farther than this right now. I don't have any grandchildren yet in my side. My kids were also 11 years younger than my brother's kids, so there's a big difference in
My
age.
family tree is weird.
Yeah.
I was
lots of
born
them
late compared to everyone else.
are.
Because my cousin is 30.
That's exactly what it is, and my family, my kids are at least 11 years younger than their cousins, so. Let's see, okay, so there's a couple other words from 5-6 that you need to know. The complement of the probability. Okay, so say the event we did was throwing a die divisible by 3. Okay, we know there are 2 chances out of 6 because the number 3 and the number 6 are both divisible by 3. Okay, so the complement is the exact opposite. The complement is just the opposite event, which be not throwing a die divisible by 3. So the opposite, which would be not throwing a die divisible by 3. And if there's 2 out of 6 that are divisible by 3, there would be 4 out of 6 that are not divisible by 3. So this is the complement. This is the event. Okay. Notice that they add up to 1. So complements always add up to 1. That's the way you can find them. Complements.
Are we still on 5-6 or 5-7?
Yep.
Okay.
Up to 1, 100%. Okay. So that's one way of looking at it. That's what the complement is. Sometimes finding the complement is easier than finding the actual probability of something. Okay, so that's why we define complements, because sometimes finding that complement is way easier than finding the event, and so we can just subtract it from one and we find the other one.
Yep.
Okay, that's when you get into more complicated stuff. Okay, the other thing in 5-6 is that they define odds. Odds is actually the probability of an event. So this is the formula. What this says is probability of an event and it's divided by the complement. Oops. So this is the complement of that event. This is kind of like a ratio because the odds, if we talk about boys to girls, there are 7 people. The probability of that is 2 sevens or 2 girls is going to actually reduce down to 2/5 because there's 2 out of 7 that are girls in our class and there are 5 out of 7 that are boys. These are complements of each other. If you're a girl, you're not a boy. If you're a boy, you're not a girl. So they're complements of each other. That reduces down because if I flip these and make them improper fractions, it will reduce down to 2/5. Okay, so they're definitely, odds is very much related to ratios. Okay, gives you the ratio. Okay, so odds are really a ratio. Oops, a ratio. So if you hear that the odds which you should never bet. But the odds on a game or a football game, you might hear that. If it's 4-1, there's 4 chances of the first team winning compared to 1 chance of the other team. So it would be 4-1. Maybe this is the Seahawks, and this is the Cowboys.
Is that a different sport?
That's
Football. Football.
Wow,
Seahawks and
football.
Cowboys. Okay, so the ratio of a game when these two are playing is the chances that 4 more chances to win by the Seahawks to 1. This is used in betting, so that's not something you really want to know, but it is a way of saying what the probability or the odds are that a certain team will win. Okay.
Are you
So it's-
choosing favorites on the Seahawks?
I
No,
don't think the Seahawks
I
are
really
actually a good team.
they aren't too bad. They're actually winning a few more.
Yeah.
So I do keep up with it because my husband likes football, so I have to keep up with it to be able to talk to him. Do those kind of things because you're married to somebody that likes those things. So those are some of the other things that they talk about in 5.6. Okay. So in 5.7, it's kind of what I've already talked about. It's kind of going back and reviewing it. Okay. It's discussing the difference between probability and relative frequency. Probability is theoretical. Relative frequency is done by experiments. So it shows that they did this experiment with throwing a dice. So the theoretical probability would be 1 out of 6, 1 out of 6 for a 1, for a 2, for a 3, for a 5, and a 6, 1 out of 6, 1 out of 6, 1 out of 6. Though that's the theoretical probability, because we know there's 1 out of 6 sides on the dice. 2 out of 6 on the dice. So the theoretical probability is 1/6. But if I do an experiment where I roll a die 1,000 times, I won't come out with exactly 1/6, 1/6, 1/6, 1/6, 1/6. I might come out with something like this. By the way, this is equal to 0.16. 0.16 is percent.
Also known as 1.6%.
Yes. Okay. If I do a count of it, I might come out with 0.24 here. I might come out with 0.16 for one of them, but I might come out with 0.13, might come out with 0.14, 0.16 again, and 0.17. Okay, so the theoretical probability and what I get in an experiment might not be exactly alike. If I do these experiments enough times, I will get close to these numbers. The more I do the experiment, the closer I will get to the numbers. But what this shows is, because they're not exactly equal to theoretical probability, when we use experiments to find our probability of things, it's not exactly accurate. Okay, relative frequency is not 100% accurate. It's a best guess. Oops. So when you hear about frequencies that are done by, or probabilities done by experiments, they're not 100% because it's not theoretical. So some things we just can't measure. We can't measure how many people exactly in the world right now have blue eyes. But we can take a good sample of people and figure out how many of those are blue eyes, and that's probably a good fear or experimental probability. It's a good relative frequency. Okay, so we use relative frequencies to predict, because that's the only way we can find them. We can't sometimes theoretically produce it because we can't count up everybody's eyes that are on the world right now. I mean, who's going to go do that? Nobody. It's too
How
expensive
many
to do.
people in the world are there?
Today's Mr. Beast challenge. We're gonna see how many people we can.
That's right. That's right. So
We stopped
the
counting
main
after
thing is realizing that a lot of what we hear is like in the chance that you have of doing this is not based on theory. It's based on experiments. And so it's not 100% accurate. That's why the weatherman can get it wrong every day. He's just going on past experience. And what these conditions are and what will likely come from that, but it's all based on relative frequency because he has no idea what are all the different outcomes. They are very, very different. But he's basing it on past experience and he's giving you a good guess because it's based on the relative frequency of if these conditions are here, then you're going to get snow. Okay, and that's how he predicts. So if a certain atmospheric conditions are present, then we might get snow. So that's why they
Snow?
snow thing. I like doing that. Okay. So that's the main thing I want you to know is if it's a true probability, it's theoretical. Now, winning the lottery is theoretical. Let me tell you, there's a slim, slim chance you will ever win the lottery. Don't waste your money.
You have a higher chance of getting struck by lightning
You
twice.
do. And I know someone that's been struck by lightning twice.
So he has a
she
has a higher chance of winning the lottery.
she maybe needs to go buy a lottery ticket.
Probably should.
I doubt it though. Okay. So the other thing that we see, and you'll see this when you do testing and stuff, based on different things, we might say, okay, this is called, my brain just went, but we do them as percentiles, percentiles. And what you hear about this is if you do testing, academic testing, which I think they do here every year, okay? If you do that, they'll tell you what percentile you fall in. And what that means is you're above, so there's usually maybe like the 100th percentile, the 90th, the 80th, or let's go by 25s, it's much easier, the 75th percentile, the 50th percentile,
And the 1%.
25th percentile, and we won't say 0. Okay, if you fall in the 100th percentile, that means you're as good as almost everybody else. That means you rank really, really high. You're like the smartest person.
In the
No.
world.
Okay.
No,
That's
you were among
the
the 100% of people,
Yes.
therefore your intelligence is lower.
all the others have smaller. Okay, they are less than what you are. If you're in the 100th percentile, you're at the top. Okay, you might not be the only one up there, but you're at the top. So like people on the SAT test, I don't know if you know what a SAT test is, but it's a college exam test. If they get an 800 on the SAT test, that's a perfect score. They're in the 100th percentile because that's the best they can get. Okay, so if they get a 500, they might be in the 50th percentile, which means 50% of people do better than them and 50% do less than them. So if you're in the 50th percentile, 50% do better, 50% do, you're right in the middle. And that's
really
not a
good.
bad place. No, we're average people. We're not brainiacs. I didn't score an 800 on the SAT test.
What did you score on the SAT test?
High, but not that. Okay, I think I was in the 90th percentile for a SAT test. That was in math. I know I was very high on math. My English was not as high, so I was probably in the 70th or 75th percentile for English, but in the high 90s for math. Okay, so that means I scored. So whatever percentile you're in, it means so many people, take it from 100, that many are above you. So if you're in the 75th percentile, you're about above 75% of the people. Okay, 25% are going to be a little higher than you. Okay, so that's how they use percentiles. And they do that on testing just to kind of give you a place of where are you falling. It's more a statistical tool for teachers to know how you're doing than in where it is as far as are you smart or not. Okay, I have a lot of arguments against tests, so don't get me started. They are not fair. They are written for a certain type of people. They are better scored if you know how to take a test. Some people are just better expressing answers in that way. There's all sorts of things that go into test taking, and I do not like it to be the only thing that you ever get scored on, because tests are not always the most accurate way of doing it. Okay. Complications, if you do not write well or have a hard time getting things on paper, you're going to do less well on a test, because it doesn't necessarily show what you can do in your brain or what you know, because you just have problems writing it. So it's unfair in some ways. Okay, so testing to me is not the ultimate all way. There's different ways to check and see how a student is doing. Hence why I give projects, so that people that are not as good on math on a test can do projects which you don't have the pressure on you to do, because you get to do it at home, you get to ask people, you get to work with people, all that kind of stuff. And so that's why I do projects also, so that you can explore how do I work with this. Okay, so that was 5-7. That's really all that they go to is into the percentiles. They show the percentiles of height of different NBA players. So they'll be asking you some questions about that. Where do the NBA players fall? I don't know when this was taken, but you can find out what percentile they're in and stuff like that. Okay, take a break. You guys need it.
I need it.
I need it.